Now today's lecture is GLS, generalized least square technique, is nothing but two-stage least square. In the non-spherical model, y, that is dependent variable, is equal to x into beta plus u, and here expected value of the error term is 0 or null, and expected value of u and u transpose, that means error and error term transpose, is equal to omega sigma u square into omega. In the two-stage square technique, in the first stage we transform non-spherical model to spherical model in some way to transformation matrix use, and rho inverse rho transpose rho equal to omega inverse, omega is the weight. In the second stage we use classical least square technique to estimate the parameter of the transformed or new model. So here in the non-spherical model, y is equal to x beta plus u. So first stage, pre-multiply both sides in the non-spherical model by transformation matrix P. So py is equal to px beta plus pu. It's equal to py, it means y star, is equal to px means x star into beta plus pu means u star. To be the new model spherical, to find to must satisfy this condition, expected value of u star is equal to 0, expected value of u star into u star transpose is equal to omega sigma u square I. So there is main difference between spherical model and a non-spherical model is that when we consider the non-spherical model, then expected value of u dash, it's equal to sigma u square into omega, but in the when the model is transformed into non-spherical to spherical here, then the expectation or mean value or expected value of u star into u star prime is equal to sigma u square into I. That is major difference between spherical and non-spherical model. In the next slide, that the in the next slides proof that the expected value of u star is equal to 0 and expected value u star into u star prime is equal to sigma u square I by some steps. Expected value of u star equal to expected value of pu, where p to the outside, and expected value of u, we know that expected value of u equal to 0, so p into 0 equal to null, and expected value of u star prime is equal to expected value of pu into u prime p prime, because we know that u star equal to pu and u star prime equal to p prime u prime. So same values are used here, so both the values are taking in the expectation. So expected value of pu into u prime p prime, or it is better to write that so ultimately p into expected value of u transpose into p transpose, p into, we know that in the non-spherical model expected value of u transpose, it's equal to sigma u square into omega into p transpose. So sigma u square taking in the outside and p omega p transpose, it is sigma u square into I, because it's equal to ultimately I. So getting the value from here, new model is a spherical model. So P transpose P is equal to omega inverse. We know, and pre-multiply both side by omega. So if we multiply in this equation, multiply by omega, so omega p P transpose P equal to omega inverse, it's equal to omega P transpose P equal to I, because we know omega into omega inverse follow the same rule, A into A inverse equal to I. So ultimately the value it's I. So again pre-multiply by P, and P into omega from this line, P into omega into P dash P into equal to P into I. So pre-multiply both side by P inverse. So post multiply now in this line, P into omega into P dash into P inverse is equal to Pi into P inverse. So same here, that P into omega into P transpose into I, because we know that the last two term P into P inverse is equal to I, and Pi from this line P into I into P inverse, it's equal to P into P dash P into P inverse. So P into P inverse is equal to again idempotent matrix. So it's the value will be P from this line, P into omega into P dash is equal to I, because we know that P into P inverse is an idempotent matrix. Now we are coming to the second stage. Here use classical least square estimation technique, and the new model is spherical model. That is why we consider star y star equal to x star beta plus u star beta hat is equal to we know normally that beta hat GLS is x transpose x inverse x transpose y same, but only difference is the star value. So x transpose x star transpose x star whole inverse into x star transpose y star, it's equal to, we know the values, x transpose P transpose P into x whole inverse into x transpose P into y, where P transpose P equal to omega inverse. From where we get the value, that means this line, nothing but we just multiply P transpose P in the middle of each term, and hence GLS is nothing but 2 SLS, that means two stage least square technique. So variance covariance matrix of U, it's equal to sigma u square omega, but we can represent the matrix as root u equal to expected value of u into u transpose is equal to, it's a matrix format, n cross n matrix. We can write W11, W12, W1i, it's or we can say in general W1i, W2i, W3i, Weni. That means W11, W12, W13 up to W1n. In the second row, W21, W22, W23 up to W2n, and ultimately n row, Wn1, Wn2, Wn3 up to Wnn. It is n cross n matrix. The number of unknown is n plus n minus 1 plus n minus 2 plus n minus 3 up to 3 plus 2 plus 1. So if we just arrange this addition, so we get 1 plus 2 plus 3 plus up to n minus 3 n minus 2 plus n minus 1 plus n. So the formula is n into n plus 1 by n. So for n is greater than 1, then n into n plus 1 by 2 is greater than n, if n is greater than 1. So the number of unknown is greater than the number of equation, so the system becomes indeterministic. If number of unknown is greater than the number of observations, so we get the indeterministic result. To overcome the indeterminacy in the system of the 2SLS model, we are imposing zero or non-zero restriction in the dispersion matrix. There is two cases. Expected value of u transpose is equal to expected value of first row u1 square u1 u2 u1 u3 up to u1 un, second row u21 u2 square u2 u3, it's up to u2 un, and similarly nth row un u1 un u2 un u3 un square. So u1 square u2 square u3 square up to un square, these are the variance term, and u1 u2 u1 u3 u1 un, these are the covariance term, variance covariance term. So we can also write in this way that u11 u12 u13 n cross n matrix, this matrix, and so the variance term it's w11 w22 w33 wnn, and the variance covariance term it's 0. So where w11 it's not equal to w22, it's not equal to w33, it's not equal to wnn, so variance term are not equal. So there is a problem of heteroscedasticity with no autocorrelation. That means covariance term, covariance of u1 u2 is 0, covariance of u1 u3 is 0, covariance of u1 un is 0. So the variance term is non-constant, that means it is not follow the homoscedasticity, but there is a problem of heteroscedasticity in case 1, but no problem with the autocorrelation. And in the second case, case 2, expected value of u transpose is equal to u11 u22 u33 unn. Here u11 u22 u33, all the values are same, so there is no problem of heteroscedasticity. So case 2 follow homoscedasticity, but there is a problem of autocorrelation because the covariance term here already mentioned not equal to 0, and the up to nth value it's also not equal to 0, so the covariance term it's not equal to 0, so there is a problem of autocorrelation.